Hello everyone, and thank you for tuning into my presentation. My name is Hiba Latifi and I am from KAIST in South Korea. In this video, I will be talking about our paper for ICRA 2020, Mini-Batched Online Incremental Learning through Supervisory Teleoperation with Kinesthetic Coupling, done in collaboration with the German Aerospace Center and the Technical University of Munich. So ever since its inception, there has been a lot of progress in teleoperation, mainly because it is inevitable. Due to the recent advancements in technology, its application domains have expanded to more general areas. But classic teleoperation requires highly skilled operators. Additionally, it poses a high cognitive workload. To mitigate this problem, researchers have proposed shared teleoperation, thereby adding an additional human operator to reduce the workload of a single operator. But it is a very costly solution. Recent advancements in AI and human-computer interfaces have sought to replace the additional human operators with an autonomous artificial agent. But in order to generate this artificial agent more swiftly, one of our previous studies capitalizes on the notion of transferring human skills to a robot via learning from demonstrations through teleoperation. We then paired this agent with the human operator in order to ensure the overall task success and reduce operators' workload. But when there is a slight change in the learned task or the environment, that variation can also be dealt with through the human-agent shared teleoperation, even though it is very laborious and workload intensive. But how to identify the intention of human operator when sharing control with the agent in real time? One of the tools for this is called Dynamic Authority Distribution, or DAD, that employs a one-way energy monitoring concept, thereby observing the inflows and outflows of energy from the operator to determine their intention. This is how it works. So suppose an autonomous agent is teleoperating the slave, but there's a need for a human to intervene in, say, x-axis motion and take control from the agent on the fly. The human starts exerting force through their master device against the agent's motion, and subsequently the force and the ultimately energy value in x-axis increases. Hence the human's authority in x-axis is also increased, thereby making the agents decreased complementarily. But how does the human know how much force to exert to take control in the middle of the execution? And that is through the kinesthetic coupling force between the human and the agent, enabled through the haptic interface of the master device. So here we are showing how in a human-agent shared teleoperation setting, humans' kinesthetic coupling plays a vital role in determining when and how they perceive the agent and the slave environment, shown here as the coupling force. In addition to shared control, there is another way to account for learned tasks variation, and that is through incremental learning. Existing studies majorly employ kinesthetic teaching, and even for partially updating the learned agent, a completely new full demonstration has been used. The model is usually updated offline, and some of the approaches use multiple demonstrations to assert a modification. We propose mini-batched online incremental learning through supervisory teleoperation with kinesthetic coupling. Our proposed approach makes use of a partial teleoperated demonstration in mini batches for online incremental learning. And for that, we propose a modified expectation maximization, or EM algorithm, for partially updating our learned Gaussian mixture model, or GMM, online. In our approach, we employ DAD and kinesthetic coupling for supervisory teleoperation. So how does it all work? First, we use teleoperated demonstrations to generate a learned autonomous agent. We then let the agent reproduce the motion online while human supervises over the agent. Whenever there is a modification in the task, the human dynamically takes over through DAD and provides a partial demonstration while accounting for the task variation. In this time, the learned agent is also modified through online model updates through our proposed EM algorithm. Once the partial modification has elapsed, meaning the reason for intervention has come to pass, human gives back the control to the agent and the agent takes it from there henceforth. And this keeps on going in an infinite loop until there is any other modification needed in the agent while the system is still up. In contrast to conventional approaches, our proposed approach uses a partial teleoperated demonstration for model update, which has been understudied in the literature for partial modification. Secondly, it applies to non-obstructive repetitive tasks. For example, in our case, a 4-hole peg-in-hole task which never ends. Also, it updates model using many batches of data points from the partial demonstration. Each single batch of points is then fed into a proposed single iteration based EM to perform the model updates in an online manner while the system still continues its operation. And lastly, but most importantly, we propose a modified EM algorithm for updating model using a partial demonstration. So suppose this is our initial demonstration for generating the agent and we train a GMM through this. Now when we input a partial demonstration, we would expect the initial model's Gaussians to correctly assign responsibility for generating those new data points. For this, our proposed modified EM's expectation or the E step includes the marginal probability density function or PDF along the phase variable as well, in order to account for the correct assignment of responsibilities of relevant components when using partial demonstration. Now let's dive deeper into how our modified EM works using mini batches of a partial demonstration. For this, we run a single round of our EM for each small batch of the new data points for updating the model in an online manner. Secondly, as mentioned earlier, we introduce a modified responsibility term in the E step having probability along the phase variable. The reason for this being, the GMM components are usually concentrated around the initial demonstration, and it is possible that during the incremental learning, the new data points coming through the partial trajectory are far away from the already learned GMM, which is the case here. Since Gaussians are exponentially decaying function, there is a possibility that for the new data point, they have almost equal or near to zero probability density or PDF values for all Gaussians. This could lead to an equal responsibility assignment for the new data points in the conventional EM. To solve this issue, we take marginal PDF over the phase variable and add it to our E step, shown here in red, so that the responsibility of the Gaussians for generating those new points is valid and not zero for all the new points. This can also help to deal with the case of significantly deviated new data points. This is the experimental result of our proposed approach. Here we show 3 consecutive cycles of the peg-in-hole task, original model behavior, incremental learning cycle, and the modified model behavior. So in the first cycle, the agent dominantly controls the slave with the initially learned behavior, while human only supervises with no intervention. We then change the task setting and block the first hole. Now at the start of the next cycle, human takes authority from the agent and defines a partial demonstration. During the same time, the model gets updated. Now in the next cycle, the human doesn't need to intervene again. The dominance is low, so the newly modified agent keeps control of the task as per what it had learned in the last cycle. Moreover, we evaluated our approach subjectively against 2 other experimental approaches shown here as 1 and 2 to see how it fares in terms of mitigating the human operator's workload during teleoperation. And our approach with the kinesthetic coupling reduces human operator's workload significantly by elevating his/her status to that of a supervisor. In conclusion, we have proposed a mini-batched online incremental learning through supervisory teleoperation approach that has a modified EM for a partial demonstration. Thank you for watching and feel free to reach out to us.